So suppose we have an experiment where we're going to be rolling a 6-sided die. And we have two events. So event A is rolling an even number, or rolling a 2, 4, or a 6. And event B is rolling either a 1 or a 2. And our question now is we want to know the probability of an event satisfying A and B, so both of them. So just looking at their definitions, we can clearly see right away that if we roll a 2, then both A and B have occurred. So we want to know what the probability of that is, and what the probability of A or B occurring is. So it's not 100% because if I roll a 5, or if I roll a 3, then A and B have not occurred. Otherwise, it looks like they have. So we want to know, in general, what the probability of both of these are. So if we draw a Venn diagram to represent these two events, we can have one circle for A. So that's going to be event A. So anything that happens inside this circle satisfies event A. So that's either a 2, 4, or 6. Then my second circle satisfies B. So that's going to be either a 1 or a 2. And then in the middle is what satisfies both events. So that's going to be 2. In the middle is what's common between both of them. So now we can define a few things. Number 1, we have the concept of an intersection. An intersection is the common ground between the events. So the intersection is this purple region. That's your intersection. And the way we write that is A and then a little n, or an upside down U, B. That means what's common between A and B. And in this case, that's equal to 2. Because 2 is in B and 2 is in A. And so if we wanted to know the probability of A and B occurring, PA and B, that's the same thing as saying P of A intersection B, because whatever is in the intersection satisfies both A and B. We can also define something called a union. So a union is your OR case. So it's either A or B. So in this case, our union is everything inside these two circles. Since everything inside this circle satisfies either A or B. If it satisfies both of them, then it still satisfies A or B. And if we wanted to define that, we write it as A U B, and that would be equal to 1, 2, 4, or 6. Any of those would satisfy either A or B. If you're not 1, 2, 4, or 6, so if you're 5 or 3, then neither A or B is satisfied. Finally, we have one more topic, which is called the complement. And if we take the complement of any event, you write it as, for example, if we take A, if we wanted to take the complement of A, it's A and then subscript or superscript C. If you want to take the complement of B, same thing. And what this means is it's not this event. So AC means an event that is not A. So since A is equal to even numbers, so 2, 4, 6, its complement, AC, would be odd numbers, so 1, 3, and 5. So to actually calculate the probability of unions and complements, and then we'll get to intersections later, we're going to draw our Venn diagram again. So we have event A, and then we have event B. And we want to know the probability of A or B occurring, which is the same thing as A union B. So that's this entire red region, both circles. And that's equal to the probability of A occurring plus the probability of B occurring minus the probability of both of them occurring. And that should be a B. Now the reason we have to subtract is because when we add A, we're adding one of the circles. And then when we add B, we're adding another circle. But in that case, we're accounting for the middle region twice. So if you look at building the Venn diagram, our middle region is right here. So I'll rewrite that with a different color to make it more clear. We have the common region between them is already accounted for when we add A. So that common region is already inside the probability of A. So when we add B, we're adding it twice, but we only want to add this slice of B. So we subtract because we're accounting for it twice. So as an example, from the last page, we had A was equal to even numbers, so 2, 4, or 6, and B was equal to 1 or 2. So P, A, or B was equal to P of 2 or 1, 1, 2, 4, or 6, which is equal to probability of A, which is 2, 4, 6, plus the probability of B, which is 1, 2, minus, since now we're accounting for this 2 twice, which is the middle ground between A and B, we're accounting for it twice, so we subtract it. And if you actually calculate this, from the definition of probability, we have 4 successes over 6 total events. That's equal to 2/3 chance. The probability over here, so of even numbers, you have 2, 4, 6, which is 3 out of 6, or 1/2, plus event B is 1 or a 2, which is a 2 out of 6 chance, or 1/3, minus the probability of rolling a 2 is a 1 out of 6 chance, and that also equals 2 out of 3. Now the second thing we can talk about is the complement. So we said that since A is equal to even numbers, its complement is everything or all events that are not A. So that would be odd numbers, 1, 3, and 5. If we get any of these, then event A did not occur. So then if we look at the union between them, so A's complement, or A, that's going to equal the sample space. Since we have everything that's not A plus A is going to equal everything again. And you can see that if we add 1, 3, and 5 to 2, 4, and 6, we get 1, 2, 3, 4, 5, 6, which is all the possible rolls. So the probability of AC or A is equal to P of the sample space, which is equal to 1. So 1 is equal, if we use now our expression over here, it's equal to probability of A's complement plus probability of A minus the probability of A's complement and A occurring. Now we need to think about this. The probability of A's complement and A occurring at the same time. A is an event, and A's complement is everything that's not A. So any event that is not A. So if A's complement occurs, then A did not occur. So they will never both occur at the same time. So this is equal to 0. And another word for that is mutually exclusive. So whenever the intersection between two events is 0, that means the two events are mutually exclusive, and that means they cannot both occur at the same time. So in other words, if we isolate for the complement is equal to 1 minus the event itself. So in this case, the probability of rolling odd numbers is equal to 1 minus the probability of rolling an even number, and that means we have 1 minus 1/2, or 1/2 once again, which makes sense. Before we start talking about the probability of intersections, we first need to define the concept of conditional probability. So conditional probability is essentially asking the question, what is the probability of some event under the condition that another event has already occurred? So it's easier to understand with an example. So if we return to our two events, A, which was 2, 4, or 6, and B, which was rolling either a 1 or a 2, the probability A given B, so this line over here simply means given. So the probability of A given B is essentially saying given B, so that means you rolled already. You know that you rolled 1 or 2. So given that, now what is the probability of A? So given that you rolled a 1 or a 2, what is the probability of A? So the way to solve this is that we know we rolled a 1 or a 2. In the case that we rolled a 1, then A did not occur. In the case that we rolled a 2, then A did occur. So the probability of A, given that we rolled a 1 or a 2, so given B, is 1/2. Because we can either have rolled a 1 or a 2, but only the 2 counts as a success. So it's 1/2. Now we can remember that the probability of A was 3/6, or also 1/2. And so the probability of A given B and the probability of A are the same. What this means is that the probability or outcome of A does not depend on event B. And that means A and B are independent. They do not depend on each other. Now if we define a third event, so we'll call that C, and we'll say that C is either rolling a 2 or a 4, then the probability of C given B, so C given B is once again, if we rolled a 1, so we'll go over that process again, we know that we rolled B, we're given B, so we either rolled a 1 or a 2. The probability that C also happened, if we rolled a 1, C did not happen. If we rolled a 2, C did happen. So it's the same thing. The probability of C given B is 1/2. But the probability of C occurring on its own is 2 events, 2 or 4, out of all total events, which is 6 possible rolls, which is equal to 1/3. So in this case, the probability of C given B is not equal to the probability of C, which means that C depends on B. The outcome, or probability, of C depends on B, which means C and B are dependent. Now if we draw our Venn diagram one last time, so we have A, and we have event B, but this time we're going to draw it a little bit differently. You can see that the size of this intersection region plays a role in the probability of A occurring given that B occurred. If this intersection region is very large, then the probability that A occurred given B is also large. If the intersection is very small, then the probability of A occurring given that B occurred is also very small. For example, if we have mutually exclusive events, which means they have nothing in common, so we have event A, and we'll say we have A's complement. So everything that is in A's complement is not A, so they share nothing in common. Then the probability of A given A's complement is equal to 0, because we know that if A's complement occurs, then A certainly did not occur. For example, if we rolled an odd number, the probability of getting an even number, given that we rolled an odd number, is 0. So now with that intuition, the formula we use for the probability of an intersection, so the intersection between two events, which is the same thing as P, A, and B occurring, that's equal to the probability of A, or the first event, multiplied by the probability of B, or the second event, given that A occurred. That's our formula. And if we have an example, so if we go back to our event A, which was getting a 2, 4, or a 6, and then we had event B, which is getting either a 1 or a 2, the probability of event A and B occurring is the probability of event A, which is 1/2, since it's 3 divided by 6 total outcomes, or simply the probability of an even number, so 1/2, multiplied by the probability of B given A. So if we know we have A, so we know that we rolled an even number, then the probability of B is going to be 1/3, because if we rolled a 2, B happened. If we rolled a 4, B didn't happen, and if we rolled a 6, B did not happen. So 1 out of 3 times B occurred. And if we multiply these two together, we get 1/6. And if we look at simply the outcome of A and B, that's the same thing as saying you rolled a 2. And if we divide the successes by the number of trials, a 2 is 1 possible success divided by 6 trials, and so P, A, and B is equal to 1 out of 6, even by our first definition of successes divided by total trials. And so now you can see that if we have two dependent events, the probability of A and B is equal to probability of A and then the probability of B given A. So first we get A, and then we see the probability of B given A, multiply those two together, and we'll see the probability of A and B occurring. If we have two independent events, then PA and B is equal to PA, and then PB given A, since they're independent, PB given A is simply equal to PB. So PA and B is equal to PA times PB, which is why when you're rolling or you're flipping a coin twice, for example, flip coin twice. On your first trial, you can either get a heads or a tails. On the second trial, you get a heads or a tails once again. So the second trial, trial 2, is independent of trial 1. So in that case, the probability of getting heads the first try and heads the second try is equal to the probability of heads the first try multiplied by probability heads the second try, which is equal to 1/2 times 1/2, or 1/4, which we can see is correct since 1 out of 4 of the events is getting heads twice. So now we're ready for an example. An experiment consists of flipping a fair coin, then rolling a 6-sided dice. In part A, we're asked, what is the probability of rolling a 6 given that we already landed on heads? So the probability of rolling a 6 given that we landed on heads. If we think about this, we're tossing a coin and then we're flipping a dice. So the two events are independent. They're not connected to each other whatsoever. So then the probability of getting a 6, given that we already landed on heads, is the same thing as getting a 6 in the first place, which is equal to a 1 out of 6 chance. Part B then asks, what is the probability of landing tails, then rolling a 2? So the probability of tails and rolling a 2. Since the two events are independent, well, first we can say that this is the same thing as the probability of landing tails and then the probability of getting a 2 given that we landed tails. But we just saw that the events are independent, so this is the same thing as the probability of landing tails multiplied by the probability of rolling a 2, which is equal to 1/2 for getting a tails, and then 1/6 for rolling a 2, which is equal to a 1/12 overall chance. Now our second example has an aquarium that needs to feed a goldfish and a catfish daily. The goldfish needs to be fed 20% of the time, while the catfish needs to be fed 70% of the time. And if the goldfish needs to be fed, it's 90% likely that the catfish also needs to be fed. So right away we have some givens. So the probability of the goldfish needing to be fed is 20% or 0.2. So we'll write that as P of G. P of C, or the probability that the catfish needs to be fed, is 70% or 0.7. And the probability that the catfish needs to be fed, given that the goldfish needs to be fed, is 0.9. And right away you can see that since P of C does not equal P of C given G, then C and G are dependent events. So our question is, what is the likelihood that both need to be fed at the same time? So that's the same thing as saying P of G and C, so the goldfish and the catfish need to be fed, which is the intersection between them, which is equal to the probability that the goldfish needs to be fed multiplied by the probability that the catfish needs to be fed given that the goldfish needs to be fed, which is equal to 0.2 multiplied by 0.9, which is equal to 0.18. So that's how likely it is that both need to be fed at the same time. Now we can also ask the question, what is the probability that either one needs to be fed? So the probability of either the goldfish or the catfish needing to be fed. And that's going to equal the probability that the goldfish needs to be fed plus the probability that the catfish needs to be fed minus the probability that both of them need to be fed, since that would be accounted for twice. So that's equal to 0.2 plus 0.7 minus 0.18, which is equal to 0.72. So the probability that either one would have to be fed, so you only have to feed one of them, is 0.72.